one of the things that you might be interested in is trying to figure out if there's any type of relationship between two variables. Like mentioned this before, the ACT coming out of high school and first year GPA as a college student. There might be some relationship between those two variables, right? Hello, how are you? All right. Anyway, so that's what the covariance tries to measure a little bit. The motivation that I did in the video was trying to talk about that least squares line idea. And then what pops up in that least squares line is that measure for the covariance. So to write down the definition of covariance, your book uses the notation COV of X and Y. Remember that our definition of variance, literally the definition of variance of a random variable is expectation of the deviation from the mean squared, right? Oh, did I give you one? Sorry. Here you go. It's the deviation from the mean squared, right? That's what we do for covariance. You didn't get one either? So we define our covariance almost in a similar fashion, except that we're looking at a covariance, right? So we want to think about a quadratic piece almost, pardon me, multiplying two things together. But since we're trying to figure out an interaction between the variables, what we do, goodness gracious, sorry, is look at an expected value of the deviation of X from its mean times the deviation of Y from its mean. So that's our definition of covariance. It's the expectation of the product of the deviations. Notice that, like I said, that kind of matches up with how we defined variance in the first place, right? Basically, variance of a variable is just the covariance of it with itself, right? If you look at the definition, okay? So it matches up with our idea of variance. Of course, just like what we have for our idea of variance, we don't typically compute covariance in this way. This is the definition, but usually we have a working formula, just like what your working formula is for the variance. What was our working formula for the variance for calculating it? Yeah, expected value of x squared minus expected value of x quantity squared, right? So let's see if we can rewrite this using our properties of expectation and see if we get a similar looking formula. So distributing everything we'll get pardon me. We'll get the product of x and y. We'll get the mean of y times the x. We'll get the mean of x times the y, and then the sum of the product of the means. But we know that for as far as expected value goes, expectation goes, what can I do with the expectation relative to the sums and differences here? Split it, good. And then if I have a constant inside the expectation, what can you do with the constant? Pull it out, and expected value of a constant is the constant, right? Pardon me. My goodness. All right. So these are random variables, so I can't break that up at all. But after we've calculated the mean, that's a constant. So I can pull the constant out in front. So I have mean of y times expected value of x. The other one, I can pull out the mean of x, and I have expected value of y. And then again, the mean of x and mean of y are constants, so the expected value of those is just that constant. But again, what's another name for expected value of x? mean of x, right? What's another name for expected value of y? Mean of y. So notice that these three terms, ignoring the 9 signs, those three terms are all the same, aren't they? So I can combine them all together, and I'll write it in terms of expected value versus the means. You end up with expected value of xy minus expected value of x, expected value of y. This looks like our working formula for the variance, doesn't it? Because if you think of x and y being the same variable, you have expected value of x squared minus expected value of x quantity squared. It looks like the same formula, which is nice. All right, so let's go over to this first problem. You can do covariance in both the discrete and the continuous cases. Pardon me. Sorry. We can do the covariance in both the discrete and the continuous cases. It would be defined analogously because you're doing sums versus integrals, depending on which ones you're doing. So let's just go through this. So the first part is going to review what we mean by marginal PDF. The second part is going to compute old stuff that we've done and then the new stuff. And then we'll talk about the least squares regression line, which was in the video that I asked you to watch. So let's look at this PDF. We've got f of xy equals 2. And then we've got a region that says that your y needs to be less than or equal to your x, and both have to be between 0 and 1. So if I graph the line y equals x, I got that diagonal line. Do I want to shade above or below that line? If the y is less than or equal to x, we want to go below, right? So we're looking at that triangle. First question I'll ask that's not on the paper. Are x and y independent or not? Are they independent or dependent? You don't tell by looking. Are they independent or dependent in this case? They're dependent because why? It's not rectangular, right? Remember, it's not enough for them to be independent because it's rectangular, but you know automatically if your sample space isn't rectangular, they can't be independent, right? What I mean by that is, if your x value is a half, can I get a y value of 3/4? No. So they have to depend on each other, right? The possibilities for y depend on what you have for the x value, and vice versa. Okay. So they have to be dependent. They don't have a choice. All right. So let's do our marginals. Remember, for our marginals, we have to integrate over all the possible y's to get our marginal for the x. And then likewise, to get the marginal for the y, we have to integrate over all the possible x's. So in the first case, my y bounds need to be in terms of x. In the second case, my x bounds need to be in terms of y, right? So when I'm integrating with respect to y in this first case, that means I'm holding my x constant, right? What are your bounds for y holding x constant? 0 to x, good. 0 to x, because I have to go up and hit the line. The function is just 2. So we'll get 2x when we're done. I'm sorry, I don't know why that set me off. Goodness gracious. Apparently talking for an hour doing virtual interviews makes my lungs messed up. Everybody okay with where those bounds are coming from? Okay. For the other way, let me erase this red if I can. Good, I did. And let's go the other way. The other way, I need to integrate with respect to x and hold my y constant. Going that way. What are your bounds in that case? Yeah, y to 1, right? The lower bound is y, x equal to y. The upper bound is x equal to 1. same function we're integrating with respect to x here. And in this case, you'll get 2 minus 2y when you're done. Or 2 times 1 minus y, whichever way you want to think about it. Are we okay with the marginals? Okay. All right. So then it's asking us to find those different values. We want expected value of x, expected value of y, variance of x, variance of y, and then the covariance and the correlation coefficient, which we haven't defined yet, but we will in a second. All right. We've already integrated one time. So there's no reason to go back and do a double integral for expected value of x, because now I have the PDF for x, don't I? I've recovered the PDF for x. I've got the PDF for y. So to figure out each of those means and the variances, I might as well just integrate from 0 to 1 my 2x dx. And for the y, I might as well integrate from 0 to 1 of 2 minus 2y dy. I already have my PDFs. Oops, I need to multiply, don't I? Sorry. I've got to do x times the first one and y times the second one. Sorry about that. I need to take my x and multiply it by the PDF. I need to take my y and multiply by the PDF. Sorry, I forgot a term in there. I would have realized at the end when I got both answers being 1, I did something wrong. Because I would have just been integrating the PDF. This is 2x squared. So an antiderivative there is 2/3 x cubed. And we get 2/3. For your y here, you've got 2y minus 2y squared. So you should get y squared minus 2/3 y cubed. And you should get 1/3. If you've done any work in geometry or maybe physics and you've calculated centroids, you know that if you've got a right triangle, your centroid for each particular one is 1/3 of the distance the other way. What I mean by that is, if I want my y centroid, I go up 1/3. It's 1/3 of the way to the next one. If I want my x centroid, I go back 1/3, so I know that this is the point. 2/3, 1/3. If you had geometry in high school that did centroids, if you do medians, they intersect at a distance that's a ratio of 2/3 to 1/3 from vertex to side. And if you haven't done any of that, you can ignore what I just said for the last minute. Okay. Just trying to relate it to stuff that you may have already done. This mean of x and mean of y, based on your density function, should correspond to centroid. Okay, so if you've done things with centroid, they literally are the same thing. Okay. Notice in this case, I've got a uniform density function, right? My density function is a constant, so it's uniform. So it literally does match up to centroid, for what you would know for centroids and regions. It's the only reason why I'm mentioning it, because I know many of you are in physics, so I thought I'd mention it. Like I said, if you don't care, you can ignore what I said. All right. For variance, now that we've got the means, we can do expected value of x squared and expected value of y squared. Now I'm now integrating, for the x, I'm integrating 2x cubed. Anti-differentiate that, you should get a 1/2 x to the 4th. So we get 1/2. For the y squared, we're integrating 2y squared minus 2y cubed. So you get, what, 2/3 y cubed minus 1/2 y to the 4th. And 2/3 minus a half is a sixth. I know I'm doing the integrals quickly, but they're polynomials. So I'm hoping that you can do your integrals of your polynomials. To find the variance now, what do I need to compute? Good, yeah. The expected value of x squared minus the mean squared. A half is 9/18. 4/9 is 8/18. So I get 1/18 here. I do 1/6 minus 1/3 squared. Again, I can do 18ths. That's 3/18 minus 2/18. So I get an 18th. Given the way the region looks, is it surprising that your variance for each of these are the same? It's uniform over that region, and when I'm looking at my region for my x's and my regions for the y's, they look the same, don't they? Right? So I'm not really surprised that they come out to be the same number. Okay. All right. That's all review stuff, right? We've done all, this is not new for the new stuff that we've talked about. The next part asks for covariance. Well, we figured out expected value of x and we figured out expected value of y up at the top. For covariance, I need expected value of xy, right? This one I really do have to go back to the double integral. I'll need to do xy times f of xy. And I'll say dy dx. I'll do it that order. Doesn't really matter. I have to do whatever the function is on the inside here. So it says expected value of xy. So I take my PDF, my joint PDF, and multiply by xy. This is why I had to go back to the original double integral idea. You could do dx dy or dy dx, but I'm doing dy dx because, well, why am I doing dy dx? Maybe I'll do dx dy instead. No, I'll do dy dx. When it's dy, I hold the x constant first, so we know that your bounds went from 0 to x. And then your bounds for x go from 0 to 1. If you do dx dy, your bounds on the inner one here would be y to 1. We've already written those bounds, right? We did those up above. So this is not a huge surprise. Yes? Because I'm integrating with respect to y first. My bounds would have to be in terms of x. So these always have to be constants on the outside. Remember, we have to get a number when we're done. We lose a variable every time we integrate. So if I integrate with respect to y, all y's have to go away. If I integrate with respect to x, then all x's also have to go away. Remember, I'm trying to go back and integrate over the whole region. So I'm trying to describe the whole region, right? In that case, it would be 0 to 1 because your y's also go from 0 to 1. Yes. Yep. Okay. So for this one, I'm integrating 2xy with respect to y. So you get xy squared evaluated from 0 to x. Right? Because I would integrate a 2y, I get a y squared. Now I've got x cubed that we're integrating. So I get 1/4 x to the 4th. And so I get a quarter when I'm done. So then to compute your covariance, you do expected value of xy minus expected value of x times expected value of y. We computed the expected value of x to be 2/3. We computed the expected value of y to be 1/3. So I've got a quarter minus 2/9. I've got to go all the way to 36 for a common denominator there, don't I? I got a 4 and a 9. 1/4 is 9/36. 2/9 is what? 8/36. So we get a 1/36 when we're done. Assuming I did my arithmetic correctly. We'll pretend like I did. Are the computations okay? This was the first new thing we did, right? Okay, so the covariance is positive. Well, what does that mean, essentially? And this is going to go to the idea of the correlation and then the least squares bit. Let me go back up to the picture that we drew. The covariance being positive in this case basically means that there's a tendency for, as x increases, the y also increases. That's what a positive would mean, which is what we see from the picture, right? And it's a tendency, it's not a guarantee, right? As my x goes over, my y's could still be small, right? I just know that I've got, it's because again, everything's random, right? But I've got more room over here to play with, right? So as my x gets bigger, on average, my y should also get bigger. Not exceptionally bigger, because I got a small covariance, but it's not a huge stretch here to see that. Okay. All right. So let's talk about another measure for that, and that's what the correlation does. We see in this case that the covariance is pretty small, but also notice that your variances for x and y are also small, right? So the correlation hopes to give you a little bit better of a measure to see, is it really small relative to the x's and y's, or is it actually bigger? Okay? Relatively speaking, given the respective variances of x and y. So the way that you compute the correlation coefficient is you take your covariance and you divide by the product of your standard deviations. The reason why is because this comes out of the least squares equation, which I'll write down in a minute, which again is in that video that I asked you to watch for today. But this gives you a relative measure. This is saying how much do x and y vary together. This is how much does x vary. This is how much y varies. Right? So we're doing that ratio idea. In this case, pardon me, your covariance we just came up with was 1/36. The variance for each of these was 1/18, right? So you would have square root of 1/18 times square root of 1/18. Because you had to take the square root to get the standard deviations, right? So you do the square root of each of those. However, in this case, I can simplify it a little bit. Since they're the same number, that just turns out to be 1/18 on bottom, and so you end up with 1/2 when you're done. So this gives you a little bit of a measure. The closer to 1 this gets, the more correlated they are. So we call this the correlation coefficient. I'm not going to go through it all because that's what the video is for. Your correlation coefficient is always between -1 and 1, always. And the closer you get to 1, the more linearly related the two variables are. So if rho is equal to, that's a Greek letter rho, by the way. If rho is equal to 1, then they're perfectly positively correlated. If rho is equal to -1, they're perfectly negatively correlated. Closer to the one, the better is talking about correlation. Now, there's a whole thing in statistics talking about correlation versus causation. Correlation just says that they are related. It doesn't say one's causing the other. Okay? There's a joke that says that everyone who confuses correlation with causation dies. That's the joke, right? Everybody dies. It has nothing to do with confusing correlation and causation, right? Correlation just means there's a relationship. They both could be being influenced by a third thing, right? For example, pardon me. For example, if you talk about, I'm scrape it. Pardon me. Rainfall dropping over time and sales of crops dropping over time. Well, those two things are correlated with one another, but maybe they're both being influenced by some third party like the planet getting warmer all together, right? So there's correlation between those two things, but the cause of both of those things is because the planet's warming, for example. There is if you do a Google search for spurious correlations, there's a bunch of hilarious correlations of different things that are really funny that have nothing to do with each other. So if you want to laugh from a math perspective, that's kind of funny. In any event, this is how you calculate correlation. All right. The correlation part comes up with the idea of least squares. Okay. So that was one of the things, if you've done statistics at all and you're trying to get a model of one variable in terms of the other, you may have created a regression line. For those of you in linear algebra, we've been talking about least squares. It's the same idea, okay, just for a linear function. Turns out that you can calculate your least squares line in a point slope form that looks like the following. Your y is equal to the mu sub y, your mean, plus a slope piece, which I'll write down in a second, times x minus mu sub x. So in particular, if you're doing, I gotta fill in I've left the space on purpose. I gotta fill in the slope. Okay. If you're doing a regression line, you would expect that your regression line, if it's trying to give you the best guess based on your data, you would guess that it's going to go through the point that includes the mean of both of them. Because your mean is kind of your best indicator of what's going on with the data, in some sense, right? So you would expect that the line should go through the mean, and it does. But then we have to talk about the slope. Well, your slope should bear, if you think about slope from an algebra perspective, remember slope is change in y over change in x. From a probabilistic or a statistical standpoint, what might measure change in y? What might measure change in y? What has to do with variance, right? Standard deviation, variance would measure, right? So if I think about change in y over change in x, I probably have something that involves either variance or standard deviation. Turns out it's standard deviation. Now, if they're perfectly correlated, this is exactly what your least squares line would be. Okay. Now, if they're not perfectly correlated, there's going to be some shift in there, if you will. And that shift, or not really shift, but a slant, if you will. And that slant is based on the correlation. So your slope turns out to be your change in y over change in x. That's what this is kind of measuring. But then this is telling you how related they really are. So that's giving you an adjustment factor. If it's 1 or -1, then it's that perfectly correlated thing that's going to go right through your data that you collected. The closer this is to 0, the more points are going to be scattered around your line. So in our case, when it asks you to calculate the least squares line, your mean for y was a quarter. Not a quarter, that's a third. I wrote a third and said a quarter. Your mean for the y was 1/3. Your correlation coefficient was 1/2. Your standard deviations were both square root of an 18th. And then you have x minus 2/3 in there. Notice that your root 1/18 will cancel in this case. And that would be your equation of your line. I could write it in slope-intercept form if I wanted to, but that's the equation of your line. And notice in this case that your line, if I go back up to my original region here, your line would go just like this. That would be your least squares line there. If you graph this line, it would go like that. And what they ask you in the problem is that surprising based on what you have? Well, think about it. Your PDF here is uniform, isn't it? Isn't it? Yep. And we already said that the farther you go to the right, the more room you have for your y's to get bigger or smaller. So we would expect it to go up and to the right as far as it does. And also notice that since it's uniform, what's it doing to the region? Splitting in half, right? Basically, it looks like it's splitting in half, and that's not a huge surprise. Because again, the PDF is uniform, so we would expect as many things to be above the line as we would below if we were taking samples, right? If we thought about just taking a bunch of points and random sampling, I would expect to be as many things above as below for any particular x value, right? So I'd expect it to kind of just split it right in half. That makes sense from a picture standpoint. Now again, pardon me. Again, you're not looking at this necessarily in statistics, given a nice continuous region. In statistics, you would collect data and do kind of a scatter plot and then see what happens with your line. Anyway, that's more of a discussion for a different day, but I just want to talk about why we're studying this stuff. Any questions on the computations? Yes. The row? The row is, if it were this, then that means that all of your x's and all your y's follow a linear relationship. Everything would be on that same line. This is talking about how far away from that perfect relationship would it be. So if the correlation is 0, then you just get a flat line, and there wouldn't be any relationship between the two. So for example, if they're independent, there wouldn't be any relationship. All right. Anyway, that's the least squares line. I'm not going to ask you to do any more than just calculate the least squares line. That's another discussion for a different day, for the importance of it. All right. See if we can do another one here. This one's similar to the previous one. Again, just looking at how it's described to you, are the variables independent? No. Again, we don't have a rectangular region, right? So it cannot be independent. Even though, again, remember I told you that part of being independent means that you can split your PDF into two pieces with just x and just y. You still have to have a rectangular region. It doesn't matter if I can see that here, where I can split it into just x and just y, right? There's multiple pieces that go to it. All right, again, I'll draw my region to start with. In this case, I still draw the line y equals x, but now my y is bigger than my x, right? So we're up here for my shading. This says the y is greater than or equal to the x. All right, so let's go through. I'm not going to go through all of the computations because those are things that you should practice on your own. Let's talk about how we set these things up. Define the marginal PDF. We integrate over what? The y's. Good. For the marginal PDF, we always integrate over all the y's. And then with respect to y, our PDF, joint PDF in this case is 8xy. If we're integrating over the y's, we're holding x constant. So I want to need my bounds this way. In terms of x, what's your lower bound in terms of x? X. In terms of x, and the upper bound is 1, right? Y equals x to y equals 1, right? We agree with that? Are you okay with that integral, or do we need to go through it? I'd rather not spend the time on doing the integration. That's just a polynomial, all right? All right. What changes if you're going to do your marginal with respect to y? Besides changing it to integrating with respect to x, what else changes? Okay, good. Your bounds change, right? So my bounds this way, this case, I have to go this way, don't I? And now your bounds need to be in terms of y, right? Functions of y. The lowest x you see is y equal to 0, or x equal to 0, I should say, and then x equal to y is your upper bound. This okay? Yes. My y has to be greater than or equal to my x, so I'm shading above rather than below the line. What's the y? That's the y equals 1. That's my upper bound. Because my y can't get any higher than that, so that's where it cuts off. The other one, the x was cut off, right? Because it says y is less than or equal to x is less than or equal to 1. So that was my right side. This is telling me what my top side is. Okay. That part okay? If you were to set up, I'm not going to go through to, because again, you should be able to do expected value of x and expected value of y in the same way, right? Take your PDF for x, integrate from 0 to 1. Take your PDF for y, integrate from 0 to 1. Okay. Let's set up your expected value of xy. First, to do expected value of xy, I'm going to have to do that iterated integral, right? Because I've got an x and a y in there. What's your integrand going to be? We'll worry about the bounds in a minute. What is your integrand going to be? Good. xy times 8xy, right? Function times PDF, just like any other expectation, right? Still function times PDF, but it's a function of 2 variables, which is why I have to do a double integral, right? You can integrate in either order. There's nothing special about the integrand here that tells us what order to integrate with respect to. Doesn't matter. I would probably do dx and then dy, because my dx, my bounds are 0 to y for x, right? And I like a bound of 0 if I can use it. It's a lot easier to use, okay? My goodness, I don't know why I have so much issues. So I would do 0 to y, dx, and then do 0 to 1, dy. I would do it that way. If you did it the other way around, you would do x to 1 in here. It'd still be 0 to 1 on the outside, because your x's and y's both go between 0 and 1. Are we okay with the setup? I don't want to go waste the time with the computation. I'd rather talk about the concepts. Okay. Otherwise, you're just going to plug in the things into the formulas like we did in the previous problem. All right. Let's go on to the next one then. we'll go ahead and do this one. Just make sure we're all on the same page. Might be able to tell this is an actuarial exam practice problem since there's actually 5 choices there for you to figure out which one it is. Okay. All right. Again, here I would draw your region first because I'm going to have to do a bunch of integrals to get all this stuff, right? Okay. So it says that your x goes from 0 to 1, and your y is between y equals x and y equals 2x. So all the way up there. So this one asks for the covariance of x and y. So again, for your covariance of x and y, we need expected value of xy minus expected value of x, expected value of y, right? Now, in all of the previous examples that we've done so far, in every single example that we've done so far, it's asked us to calculate each of the marginals, right? It's asked us to calculate each of the marginals and then asked us for the means, right? Okay. Do I really, really, really want to do the marginal for the y? Or sorry, the x, I guess. Do I really? No, I meant the y. But when I do the marginal for y, I need to integrate over my x's, right? To get it? What's bad about integrating over your x's? There's 2 different right curves, right? I really, really, really do not want to try to figure out what the marginal PDF is for y because it's going to be piecewise. And anytime I come across a piecewise function, I've got to do it in 2 pieces if I'm going to integrate, right? That sounds like it sucks a lot. I don't want to do that, right? Nothing about this formula, though, for the covariance says I have to find the marginal for x first or the marginal for y first, either or, okay? I can still do these both with iterated integrals. So we can still write this down as an iterated integral of xy times 8/3 xy, and I'll come back with my bounds here in a second, minus my iterated integral for x times 8/3 xy, and my iterated integral for y times 8/3 xy. There's absolutely nothing that says to find the expected value of x or to find the expected value of y, I have to find the marginal first. I don't have to do that. In this case, it's hard to find the marginal for y. Not impossible, you can do it. It just takes more work, and then you got a piecewise function, so then to find the mean, you'll have to integrate over a piecewise function. And I really don't want to do that. That's more work than is necessary. All right, so let's figure out the bounds now. I can use the same bounds for all 3 integrals. I don't have to change, okay? So in particular, I'd probably want to integrate with respect to y first and hold x constant, right? I want to go this way. We agree? So what are your y's range between? X and 2x. That's the y, not a dx. And then what are your x's range between? 0 to 1. And I can do that for every single integral. I don't have to get the marginals first if I don't want to. And that makes life easier, doesn't it? Yes. Because I do not have the marginals for x and y. I'm using the joint PDF first, right? Yeah. If I have the marginal PDFs, then I only have to do one integral because I have the PDF for X and I have the PDF for Y. Right? But in this case, it's really, really hard. It's not really, really hard. It's really inconvenient to find the PDF for Y. Because to find the PDF for Y, I have to set up I have to do two pieces. And so I'll have a piecewise defined function. And then I have to do two integrals to find the expected value of Y. It's this integral that would be more difficult. That's why. Do I need to go through the integrals or can you handle those? You want to go one through? I'm not going to do all three. Which one would you like me to do? If I can do, you can do one, you can do the other two. Which of the one or the three would you like to see? The first one? Okay. The first one, what are we integrating? We've got 8/3 x squared y squared dy dx. We're integrating with respect to y. So when you integrate with respect to y, what do you get? Now notice that's going to be the exact same, not the exact same integrand. Here's the other thing you're multiplying by. This one will be an x times that, and it'll be a y times that. So it'll be different for the integrands, but this is the same concept, right? We put in 2x. I get 8x cubed times another x squared. Right? When I put in 2x, I get an 8x cubed times another x squared. So I get 64/9. Whoops, I'm going to subtract. I'll get a 64/9 x to the 5th. And then I'll get another x to the 5th. I get 8. 64 minus 8 is 56. Is that right? So I get a 56x to the 5th when I'm done. The 2 cubed gives me 8. 8 times 8 is 64. And then I get to put in a 1. I get 8 ninths. So 64 minus 8 is 56. Okay. Then an antiderivative for this. Oops. I would get 56 over 54. So I have an x to the 6. 56 over 54 is 28 over 27. So I get 28 over 27 just for that piece. This is why I didn't want to do all of them. That part okay? Let's do another. Let's do one from a discrete case. I gotta have something in here that's discrete. There we go. There's a discrete one. All right, so we've got two random variables given with a joint probability distribution. Your x's go either -1, 0, or 1. Your y's are either 0 or 1. And this particular one asks you what is the covariance. Well, let's see if I can ask a different question to start with. I know it's not related to this problem, but I ask, are these two variables independent? Okay. Remember, independent says that if I take the probability of x equaling a value and y equaling a value, it should be the product of the individual probabilities, right? Okay. So what's the probability that x equals 0 and y equals 0 according to the table? This is 0.1, right? That's right out of the table, correct? Agree? Okay. What are the individual probabilities? What is the probability that x is 0 and the probability that y is 0? What is the probability that x is equal to 0? So here is x equaling 0, all right? So your probability is 0.4 because it could be 0 and 0 or it could be 0 and 1, right? So I add those two together. How about the probability that y is equal to 0 then? It's also 0.4, right? If you multiply these two together, do you get that? It's not a trick question. If I multiply those two numbers together, do I get that? No. So are they independent? No. Okay. Okay. So this is how you could check for this particular one if they were independent or not. I randomly just picked 0 and 0, guessing they probably weren't independent. This is a guess. Yes. What do you mean? Rectangular is not the only thing, right? If it's rectangular, notice that this space is rectangular, right? So this space is rectangular, so that's not enough to tell me it wasn't independent. I actually need to see if it could be split up that way. I just picked one. I would, if those turned out to be equal, it still wouldn't be enough to tell me I have to go check them all. Okay. All right. So for covariance, then, still our formula is expected value of xy minus expected value of x times expected value of y. But rather doing double integrals in this case, since it's discrete, we would use double sums, right? I gotta do double sums. I'm probably not gonna write out all the sums. I think it's probably just easier to write out the actual values, right? Why is it easier? Well, what are some of my values gonna be? 0, right? I got lots of zeros, don't I? Okay. So for your expected value of xy here, I don't need to worry about any value in this row or any value in that column because it'll be 0 when I take x times y, won't it? Won't it? Because anything that's in this row, y is 0. Anything in that column, x is 0. So when I do that product, I'll get 0. Okay. So the only ones we need to worry about are this one and this one for that particular one. Okay. So for this one, I would have, I'll write it out. I would do -1 times 1 times 0.1. X is -1, y is 1. This says multiply them, and then multiply by the probability. What would the other one be that matters? Good. 1 times 1 times 0.2. Good. The other ones are all going to be 0. I could write them out, but I know they're going to be 0, right? Right? I know they're all going to be 0, so there's not much point in writing them. Okay. I would have, for example, if I worried about this one right here, my x would be -1, my y is 0, and the probability is 0.1. So you'd have -1 times 0 times 0.1, but I know it's 0. So I didn't bother writing it. Does that make sense what I'm saying? Just trying to cut down my work, right? Okay. What about for expected value of y? Or excuse me, expected value of x? What are your, I can either do it the long way or the short way. What isn't going to matter for expected value of x? Which values do I not need to worry about for expected value of x? the 0.1 and 0.3, right? Again, I don't need to worry about this column, do I? Because those are, well, I would take 0 times each of those, right? Okay. What's the negative 1 going to get multiplied by? A 0.1 and another 0.1, right? It's the expected value of x, right? For this x value, I've got a y that's 0, but this x value has a probability of 0.1 here and a probability of 0.1 here, right? So it's either this one or it's this one. That's why I've added, right? What's the other one going to be? Good, yep. And then I need to multiply that by the expected value of y. Which row matters for that one? The second one, right? Because all of these will be 0, won't they? Those will all go away. The only y value we have is 1. That matters. What are we going to multiply the 1 by? Good. What do we get? We get 0.2 minus 0.1. So I got a 0.1 there. This is minus 0.2 plus 0.4. So I get a 0.2. This is 0.6. And it looks like you get negative 0.02 when we're done. So we get it. That would be your covariance in that case. Is that one okay? When it's a discrete case, it's probably just as easy just to write them all out for what you get. Okay, and then trying to write out a double sum. You're not going to get anything that's huge in the discrete case. Like in this case, at most, you would have had to write 6 things out for a sum, right? Because there's only 6 probabilities. So just write them out. I wouldn't try to come up with some formula for a sum. I would just write out the possibilities. All right. Oh, let's see what else we got. Oh, this one's a good one. This one gives us a little bit of concept into what's going on with trying to find the variance of something. All right, so, and this ties into stuff that we're going to do in the next chapter. Don't worry about the fact that it's talking about anything with a profit. It says we've got independent random variables, so we're going to talk about that here in a second. And you've got a variance of 1 for x and a variance of 2 for y, and then it asks to find the variance for z. Well, let's do this off to the side, and then we'll talk about the independence part here in a second. Okay? So let's say we start with, independent or not, let's say we start with a variance of some constant times an x plus some other constant times a y. And see what comes out. Okay. Again, our working formula is expected value of the variable squared minus the square of the expected value of the variable, right? In this case, our variable is the sum of 2 other variables, but that doesn't matter. That's our formula. Agreed? Okay. Okay. In this case, I need to square out the inside. So you'll get a squared x squared plus 2abxy plus b squared y squared. Notice in the other one, I would need to split up the expected value and then square, right? Break up the expected value over the sum and pull out the constants and then square it. I'm going to do that in one step because I don't feel like doing all of it. I'd have a squared expected value of x squared. I'd have a 2ab expected value of x, expected value of y, and then a minus b squared expected value of y squared. Notice if it looks the same, except that I had to break up the expected value first, right? The other one, the square is on the inside. This one, the square is on the outside. I know I did two steps at once. Over here, same idea. I can break up the expected value and then pull out the constants. We've played with those before, right? So I would have a squared expected value of x squared. I'm going to move the other thing that has an a squared in it over with it. I've got a 2ab expected value of xy. I'm going to move the other piece that has a 2ab in it. And then I've got a b squared expected value of y squared, and then I'll have a minus b squared expected value of y quantity squared. Why did I move them together? What's a better way to write that? Good. That's a squared times the variance of x. Exactly. Right? Factor out the a squared, I have exactly the formula for variance. Let's do the last one first. What's this one? Good. Plus b squared times the variance of y. The new part would be this. What's that? What can you factor out? 2ab and it's covariance. Good. Yep, exactly right. 2ab covariance of xy. Good. This is a nice formula to be able to use. If I've got a variance of a sum, I get sum of the variances and then plus a covariance piece. Basically 2 times the covariance piece, and then you got to play with your constants. Okay? All right. So going back over to the original problem, and I'm still ignoring independent, by the way. What does that minus 5 do on the end for the variance? What kind of a thing does a plus or a minus do to a distribution? It just shifts it. Does that change the variance at all? No, so I don't need to worry about that for variance at all, right? So according to what we just came up with, your variance for z should be 9 times the variance of x plus, again, you got to square the coefficient. That's important with the negative, right? Okay. Plus the variance of y, because I got to square the negative 1. And then it'll be plus 2 times 3 times the negative 1 times the covariance of xy. It's 3 squared plus negative 1 squared. By the way, anytime you've got these variances, you should never be subtracting them. Okay? It's always going to be the square of that coefficient. All right? 3 squared plus negative 1 squared. Now you can subtract here. That's okay. 2 times a times b. 2 times 3 times negative 1 times the covariance. Okay. Yes? Oh, yeah. This part? Okay. Okay, you're welcome. Okay. All right. And they tell you in this problem that the variance of x is 1 and the variance of y is 2, right? What they didn't tell you explicitly is what the covariance is, but you might be able to guess what word is telling you about the covariance. Independent. What do you think that tells you the covariance probably is? 0, yeah. They're telling you that it's 0. Let's see why. Okay. Let's see why that's true. Remember, your covariance is expected value of xy minus expected value of x, expected value of y. That's covariance, right? Expected value of xy is the double integral over your sample space of your PDF, right? We agree? Or the double sum, discrete or whatever. But independent would tell you two things. One would tell you that your sample space is rectangular, right? Oops, I forgot my xy in front of this. Dang it. I keep doing that. First, it would tell you that your sample space is rectangular. What else does it tell you that you can do with your PDF if they're independent? It splits, right? Is a PDF of x times the PDF of y, right? We agree? And then we mentioned this the other day. If you've got function just of x, and you've got function just of y, and you've got a rectangular space, I can split this up as integrate just the x pieces and integrate just the y pieces and multiply them together when you're done. That's just a matter of when you integrate with respect to y, your x's are constant, right? So I can pull those out in front. And then this whole thing won't have any x's in it, so I can just pull that whole constant out in front. What's a better name for this first integral here? Expected value of x. This one is expected value of y. And so then I really do get 0. Okay, so this is important. Okay, if x and y are independent, then the covariance is 0. Okay, but the covariance being 0 does not imply that they're independent. Covariance is, again, kind of a measure of linear relationship. Okay? It's a linear relationship, right? You might have something that's in a nice perfect quadratic relationship, and your covariance will be 0. Okay? To give you an example of that, a simple example of that, maybe you have probably that x equals 1 and y equals 1 is a third. The probability that x equals 0 and y equals 0 is a third. Forgot what I was doing. X equals -1 and y equals 1 is a third. You can check pretty quickly that the covariance is going to be 0. Okay? But they certainly are not independent. Space isn't rectangular. Okay? For example, the only way that you can get a y value of 0 is if the x value is 0. Right? So they're not independent, but you can check pretty quickly that the covariance here is 0. Okay. So independent implies covariance is 0, but it does not work the other way around. Okay. Right, so be careful with that. But anyway, going back up to this original problem that we did, we get 11 at the very end. Is this okay? What questions do you have? Right. Let's just do this last one because it's similar, and then we will quit for the day. Because we got 3 minutes, but we should be able to do this one in 1, I hope. Okay. Variance of z. This one looks like the previous one, right? I know it's going to involve the variance of x. I know it's going to involve the variance of y. And I know it's going to involve the covariance of x and y. Right? You agree? Okay. What's going to get multiplied out in front of the variance of x? 5 squared. Good. What's going to get multiplied out in front of the variance of y? -2 squared. Good. What's going to get multiplied out in front of the covariance of x and y? -2. Good. Does that -3 have any effect on the variance? No. -3 is just a shift. It doesn't change the spread at all, right? All right, so it's coefficient on the x squared, coefficient on the y squared, 2 times the product of the coefficients for the covariance. And in this problem, they tell you the various values, right? The variance of x is 1. The variance of y is 2. The covariance of y is -1. I think I did all that right. You get 53 when I'm done? Okay. All right. So that finishes off that section. We're going to talk about conditional distributions next time. Finish that up, and then we'll jump into chapter 5. And chapter 5 will be the last, and we'll get as much of chapter 5 as we can done before the end of the semester. You have an exam in a couple of weeks, if I remember correctly. Okay. On the 2nd. I know, you're all very excited about it. And I believe our final is on the Tuesday of finals week at 11. I'll double check, but it should be the Tuesday of finals week at 11. So have a good one. Have a good week, Easter weekend, everyone.